All right. So last week we introduced, no, not last week, the week before, the last time I came, we introduced the um, course. We defined what theory of machines is. We defined what machines are, right? And then we looked at all the various elements of machines and a few terminologies here and there. We defined kinematics of machines, dynamics of machines. We defined what a mechanism is. We looked at the components of mechanisms, what links, elements, the types of links and elements. We looked at joints, okay, and the types of joints, right? And then we defined some new terminologies. We looked at kinematic pairs, okay, and we then looked at the classification of the types of kinematic pairs. Maybe that's where I will start, just so that we can have a good flow. So let me know when you can see my screen. Can you see my screen?
Yes, sir.
Okay, thank you. Now, try as much as possible. Try as much as possible not to annotate on the screen, because with Zoom you are able to make marks, to make notes on the screen. Try as much as possible not to do that, so that, because whatever you do shows up on all our screens. So we looked at the types of kinematic pairs. We said that they could be classified based on certain criteria. The first criteria will be the nature of contact at the joint. Okay, so we defined kinematic pairs as when you have two, right? Two links that are joined together such that one allows a relative motion with the other, or one moves relative to the other in a defined fashion. Okay, so we said the nature of contact at the joint, the kind of contact that joins both links will determine, you can classify the kinematic pairs based on that. And with that, we have what we call lower pairs and higher pairs. And then we looked at the nature of the mechanical constraint at the joint, okay, how these joints are mechanically held together. And with that classification, we looked at closed pairs and unclosed pairs. And then we looked at the nature of the relative motion between the links. Remember, we said that they must have relative motion between them for them to be kinematic pairs. Okay. And we sliding pairs, turning pairs, rolling pairs, screw pairs, and spherical pairs. We dealt with all of these last time I was in class, right? So we, based on the nature of contact, we said a given pair of kinematic pairs are called lower pairs if the nature of contact is surface to surface, right? If you have surface to surface or area contact between the members, then we'll call those lower pairs. And then we gave you examples in class. And then for higher pairs, we said is when pairs have a point or line contact between the links, then that's what we call higher pairs. We dealt with all of these in class, so I'm not spending much time. Based on the nature of mechanical constraint at the joint, how the joints are held together, we said if the links are held mechanically, okay, maybe with a bolt or nut or something, such that you can only separate the two links when you break that contact, such a pair is called a closed pair. They are held together mechanically. There is some force that constrains those links to be held together, okay? And then examples are screw pairs, revolute pairs, and the rest. But when the links are held together, not by mechanical means, usually under gravity or something, right? We say that they are unclosed or open pairs. Okay? They just have a point or a line contact between them. We say that they are unclosed pairs. With these pairs, you can easily push them apart. There's nothing constraining them to be, holding them firmly together. Okay? They can easily be separated. And a very perfect example is a calm and follower pair. Then, based on the nature of relative motion between the links, we said sliding pair. This is when one link is allowed to slide along the length of another. Okay, it might be inside, it might be on top of it and all of that, so far as one is allowed to slide, okay, to perform linear motion back and forth. Then we call it a sliding pair. A turning or revolute pair allows one one link to revolve, to carry out rotational motion with reference to the other link. Okay. A rolling pair allows one of the links to roll on top of the other, to roll along the other. Okay, now note the difference between rolling pairs and sliding pairs. Sliding pairs, the same surface area stays in contact. The same pair has the same contact, but it moves, that contact slides along the other. But for rolling pairs, when it rolls, different parts of that link makes contact at different times with the second one. Okay, a screw pair is just the case of having maybe like a bolt and a nut where one link, right, performs both rotary and linear motion inside another. Okay, usually they would have teeth or what we call threads, and the threads would match, and as one rolls or revolves, it moves forward or backwards inside the second pair. And then the spherical pair is, as the name implies, you have a hollow spherical space, and then you also have another sphere within that hollow sphere, and the sphere or the ball is allowed to roll in all the various axes that we have, so it can roll freely in any direction without detaching from the contact. So those were the types of kinematic pairs that we define. Now we're going to move on to look at what a kinematic chain. So please do note all these terminologies we're defining. We define a kinematic pair as an assembly of two links, okay, such that one link allows the relative motion, or one link is allowed to move relatively to the other link, right? When we come to a kinematic chain, this is when you have an assembly of many links, okay? And they are arranged in such a way that they allow relative motion between themselves. So we say that the motion has to be successfully or completely constrained. What that means is they move in a specific way. They do not have unpredictable motion. So in case you have some linkages, some links that have been connected one to another, and you cause them to move, you cause one to move, and that one causes the others to move, and their movement is indefinite. We can't define them. We can't predict them. Then such an assemblage will not be a kinematic chain. We call them non-kinematic chains. Kinematic chains have definite motions, completely or successfully constrained motion. When we move one, we know exactly how the others are going to move. Okay, so note again that these links are connected. and they are connected in such a way that they allow relative motion between themselves. As one moves, the other is also allowed to move relative to that one, okay? But that's not the only criteria. They also have to be in such a way that we can dictate, we can predict, we know exactly how the rest of the linkages move when we move one of the links. Is that okay? When we cannot say, when we cannot define how the links will move when we make an input motion into one of the links, then it becomes a non-kinematic chain. Now, there are give me a minute. Please mute your mics. Again, when you come in, mute your mic. I'm hearing a lot of background noise. If you are not speaking, please mute your mic. So there are a few relationships that hold true for kinematic chains. In fact, we use them to check if a given assembly of links is a kinematic chain or not. Okay, and these are the two equations that we check. The first equation says L equals 2p minus 4, where L is the number of links in that kinematic chain, and P is the number of lower pairs. Remember, we define lower pairs as pairs in which, the two links are connected such that they have surface-to-surface contact. And examples of lower pairs, you have spherical joints are lower pairs, revolute joints are lower pairs, screw pairs are lower pairs, right? Is that okay? A higher pair is one that allows for a point or line contact. Come and follow our higher pairs. Any rolling contact is a higher pair because it's just a line contact. All right. So if we know the number of links in a kinematic chain and we know the number of lower pairs, we check that this relationship works, that the number of links in that kinematic chain is exactly the same as what is on the right-hand side of this equation, 2 times the number of lower pairs in the links minus 4, okay? If the left-hand side is the same as the right-hand side, then it is a kinematic chain. And same thing, the second equation that we use to test is the equation that says J equals 3 over 2L minus 2, where J is the number of binary joints. Binary joints. Remember, we define binary joints as a joint that allows for two links to be connected to them. I remember I gave you an equation for finding the number of binary joints in a given joint. So where you have a ternary joint, you have a quaternary joint, they have an equivalent of binary joints, okay? I remember we said L minus 1 is, again, I've asked you guys, please don't touch your screen, okay? You're already seeing that as you touch it, you're making marks that affects all of us. Please do not interact with your screen. Just look at it. Is that okay? So that we don't have all of this on it. Okay, so L equals 2p minus 4 and J equals 3 over 2L minus 2 are the two criteria that we use in checking if a given arrangement of links is a kinematic chain or not, okay? And we said that if the left-hand side, the number of links in, for the first equation, if the left-hand side is bigger than the right-hand side, right, then what you have is a locked chain or a redundant chain. What that means is that those links, as you've arranged them, they cannot move relative to each other. They are locked. They are almost as though they were a structure. Okay? If the left-hand side of both of these equations is exactly equal to the right-hand side, then the chain is a kinematic chain. Okay? It allows for constrained motion. And that's what we define the kinematic chains are as that you have an assembly of linkages, right? And they are linked together in such a way that they allow for relative motion between each other, and that motion is completely or successfully constrained. We can predict them. If, however, the left-hand side of both of these equations is less than the right-hand side, then we have an unconstrained chain. We have a non-kinematic chain that when you move one link, the other links can move in however they choose to move. We cannot predict. We cannot define.
They choose to move. We cannot predict. They can define.
I've asked you guys to mute yourself. I'll probably ensure that
mute yourself.
We're not allowed. You cannot mute yourself. All right. I think that saves me, so nobody can unmute themselves until I ask you a question. Great. So let's take an example, and what I will do so that you can look at how I'm working, I'm going to stop sharing this screen and open a Word document that we can work with, so that just give me a minute. I'm going to open up a Word document so that we will interesting. Oh, I've gone back to my... Give me a minute. Let me change one or two settings that will allow you to see better. It's great. Now I will give me a new document here. Okay. So I'll be over there. Up to, yeah, I want 24. What did I use before? Okay. So this is example 1. Just give me a minute. I'm trying to get this up so that we can easily, well, maybe I should just... Okay. Back to Zoom. Share my screen. I want to share screen 2. Share. Okay. I'm going to allow you to be unable to mute yourselves now so that I can get feedback. Please make sure that you mute yourself when you're not speaking. But can you all see my screen? Can you see my screen? They're not talking again. You can unmute yourself, speak, and then mute yourself back. Can you see my screen?
Yes, sir.
Okay.
Yes, sir.
Thank you. All right. So when you speak, mute yourself back. That's the discipline. Once you're on mute and you speak, you mute yourself back. So we have said that example 1 says, determine the nature of the chain, right? In the figure below. And this is first example, so it's easy. Where J, and J is the number of what? What's J? We explained that before in the equation. J is the number of binary joints. Binary joints in that arrangement. P is the number of lower pairs, right? and L is the number of links. So obviously you can see that there is one, if we count these links, this is the first link, this is the second link, that's the third link, that's why L is 3, right? If we look at lower pairs, once you see this kind of pin joints, you know that they are lower pairs because it's probably revolute. This joint is a revolute joint, okay? So if we count this, that's a lower pair, that's a lower pair, that's a lower pair. There are 3 lower pairs there, right? And then when you look at binary joints, this joint has 2 links connected to it. That's one binary joint, this another binary joint, this another binary joint. So there are 3, 3, and 3. The question is this a locked chain, or is it a kinematic chain, or is it a non-kinematic chain? Is it a chain with unconstrained motion? So remember the equations, okay? What did we say the equations were? We said L, right, equals 2p minus 4. That's the first thing we're going to test. So on the left-hand side, okay, let's take the left-hand side of this equation, okay? Left-hand side of this equation is simply L. That's, sorry, simply L. And how many links are in this chain? There are 3 links, right? Right? So let's look at the right-hand side. Let's look at the right-hand side. The right-hand side of that equation says 2p minus what? Minus 4, right? This is going to be 2 times, right? P, how many lower pairs are in that joint? They've already given us in the question anyway. Please stop interacting with your screen. I don't know how many times you want me to say that. Stop interacting with your screen so that you don't mess things up for the rest of us. Okay? There are 3 lower pairs, right? There. So we simply get there and put 3 in that equation. 3, right? And from that, we are subtracting 4, okay? So this equals 2 times 3 is 6, right? Right? And then 6 minus 4 is 2. So when you look for this particular problem, the left-hand side is 3. The right-hand side is 2. So obviously, the left-hand side is greater than the right-hand side. The left-hand side is greater than the right-hand side. And we gave a criterion. We said, if the left-hand side is greater than the right-hand side, right? What kind of this thing is that? Is a locked chain. Is a locked chain. So hence, they asked us, the question says, determine the nature of the chain in this figure. And based on this one, we can say, and by the way, once this equation works, the other one too is the same thing, right? We actually usually want you to try both of them. So before we conclude, let's try the second equation and see. The second equation says that J equals 3 over 2L, right? L minus what? Minus 2. That is the second equation that we want to check. Okay, so let's look at the left-hand side of that equation. The left-hand side of that equation is J. I think this should be a small j, not capital J. Okay, J. Now, how many, what did you call them now? Binary joints are in this. Oh my God, power supply has gone. Can you still see my screen? Can you still see my screen?
No. Yes, sir.
Nobody's answering me.
Yes, we can see your screen.
Can you still see my screen?
Yes.
Yes,
Yes, I can see your screen.
Oh, I'm sure
We
the
can
answer
see
is
your
my connection.
Yes.
Say that again. I'm sure that's tough. Okay. Give me a minute. Let me sort out my power.
Interesting. Oh, seriously. Oh dear. Oh my God. What's up, guys?
All right. I believe you should be able to see my screen now. Please confirm again that you can see my screen.
Yes, we can see your screen, sir.
Thank you. Thank you. Okay, so we're checking the left-hand side of this second equation, and we saw that there are three binary joints in that arrangement. That's the left-hand side. Now, how about the right-hand side? What's obtainable with the right-hand side? The right-hand side says 3 over 2L minus 2. That's what we need to find out. Now, 3 over 2 times, how many links are there? There are 3 links, right? And then we're going to subtract 2 from that. Now, when you multiply 3 and 3, you have 9. 9 divided by 2 is 4.5. 4.5 minus 2 will give you 2.5. Okay? So for this second arrangement, you can, please, can you mute yourselves? For this second arrangement, you can also see that the left-hand side is I'll just have to do this class without getting feedback from you guys. So the left-hand side is greater than the right-hand side. Okay. And so we can conclude that this chain is a locked. It's a locked chain. That's the nature of that chain. The chain is a locked chain because the left-hand side is greater than the right-hand side. Okay, so again, let me just run through it. The example asked us to determine the nature of the chain in the figure. And they gave us, in the next examples, you will need to determine yourself, right? They gave us that J is 3, P is 3, and L is 3, and we can confirm that when you have this arrangement. This is your first link, that's your second link, this is your third link, so there are 3 L's, right? There's a joint here, and it has 2 links connected to it, so that's one binary joint. There's another joint here with 2 links, that's the second binary joint, and there's another joint here with 2 links, that's the third binary joint. So we have J to be 3. And then we need to check whether they're lower pairs or higher pairs. And you see that this, with this dot here, says that these are surface-to-surface contact, that's surface-to-surface, that's surface-to-surface. And so these are lower pairs. When we come to examples where you have higher pairs, you will see the difference in how it is represented. So we went ahead to check those 2 equations. The first equation says L equals 2P minus 4. The left-hand side is L of this equation is just L, and there are 3 links there. The right-hand side of the equation is 2P minus 4, right? And so we evaluate that expression. 2 times P. P is 3. There are 3 lower pairs, right? Minus 4. And 2 times 3 is 6. 6 minus 4 is 2. Okay? And so obviously, when you look at the value of the left-hand side and the value of the right-hand side, it is clear that the left-hand side is greater than the right-hand side. Then we take the second equation also and test it. The left-hand side is J. J is the number of binary joints in the arrangement, and there are 3 of them, right? Then we look at the right-hand side. The right-hand side, the expression says 3 over 2L minus 2, right? And 3 over 2 times the number of links in that arrangement is 3. So we plugged 3 in there. Then we subtract 2 from that operation. So when you get here, you say 3 times 3, that's 9. 9 divided by 2 will give you 4.5. 4.5 minus 2 will give you 2.5. Again, we can confirm that the left-hand side is greater than the right-hand side. And so we can conclude on the nature of the chain. If the left-hand side is greater than the right-hand side, it's a locked chain or a redundant chain, okay? It's a locked or a redundant chain. No E there. Redundant chain, right? If the left-hand side were the same as the right-hand side, then it would have been a kinematic chain, okay? And if the left-hand side was less than the right-hand side, then it would have been a non-kinematic chain or an unconstrained chain. So that's pretty straightforward. Should we try another link? Let's try another link. Example 2. Example, looks like my power is back. Give me a minute, let me change my power source. All right, thank you very much. So again, we want to take another example. Example 2. We want to determine the nature, right, of the chains given below. Okay, so I've got 2 chains. I'm going to copy and paste here. That's the first chain. Let me reduce it a bit so I find space for the second one. And this is the second chain. Okay. Can we see both chains? So let's start with the first chain. Let's start with the first arrangement. So for the first arrangement, right? Let's check how many links do we have. We have link 1, we have link 1, link 2, link 3, and link 4. So clearly L equals 4, right? L equals 4. And then let's find the binary joints. How many binary joints are there, right? There's one joint here because there are 2 links connected to that one. There's another joint here with 2 links. So this is one binary joint, this is another binary joint, this is another binary joint, and this is another binary joint. So we can say that J is 4. There are 4 of them, right? And then the lower pairs are also 4, because once you look at this arrangement, right, they are all lower pairs. So link 1 and link 2 form one lower pair, link 2 and link 3 form another lower pair, link 3 and link 4 form another lower pair, and then link 1 and link 4 form the 4th lower pair. So P again is 4. Okay, so for this first arrangement, let's check what is it. Okay, the equations to test are L equals what? 2p minus 4. Okay, we're going to do it directly here so that we can be fast. L is 4 on the left hand side equals, let's check the right hand side. Okay, no, we can't. If we do that, we will run into trouble. Let us not do it that way. Let's check the left hand side. The left hand side simply is L and it is 4 of it, right? So let's check the right hand side, right? The right hand side says 2p minus 4. And 2p minus 4 will be 2 times p. There are 4 p's there, minus 4. Okay, so this will be 2 times 4 is 8. 8 minus 4 will be 4. Okay, so you can see clearly that the left-hand side is the same as the right-hand side. Okay, all right, that's for the first arrangement. Now let's also test the second equation, which says J equals 3 over 2L minus what? Minus 2. Is it minus 2 or minus 4? It's minus 2, right? And so for the first arrangement, all these values L, J, and P are 4. So we can say here at the left-hand side, which is J, the value is 4. Okay, that's a small j. I always forget that. And then let's see what the right-hand side gives us. The right-hand side gives us this 3 over 2L. We're taking 2 out of that. So that's going to be 3 over 2 times, how many links are there? There are 4 links times 4 minus 2, right? So let's find this. We can say 2 goes into 4 2 times. 2 times 3 is 6, and 6 minus 2 is 4. Or you can say 3 times 4 is 12. 12 divided by 2 is 6. 6 minus 2 is 4. So again, obviously, the left-hand side equals the right-hand side. So this first arrangement, the first arrangement is a kinematic chain. Okay? It's a kinematic chain because the left-hand side is the same as the right-hand side. So it means that it has a successfully constrained motion. Right? Now, for the second arrangement, right, what do we find as the values of L? How many links? Let's come back to this fourth arrangement. Let's count. There's 1 link, 2, 3, 4, 5. There are 5 L's. Then if you look at the binary joints again, there are 1, 2, 3, 4, 5. 5 binary joints, 5 joints that have 2 links connected to them. And again, all of those joints connect lower pairs because that's a lower pair, this is a lower pair. So for this arrangement, we have all the values of our L, J, and P to be 5. So L is 5, J is 5, and P is also 5. So let's quickly run our equations to see what becomes of them. L equals 2P minus 4 is the first equation. The left-hand side of that equation says that L is 5, right? How about the right-hand side? The right-hand side says that 2P minus 4 will be 2 times, how many P's are there? There are 5 P's, and we want to subtract 4 out of that. Okay, 2 times 5 is 10. If you subtract 4 from 10, you would have 6. 6. Very, very interesting. So in this instance, the left-hand side is less than, is less than the right-hand side because 5 is smaller than 6. Fine. Let's check the second equation and see whether it corroborates what this one is saying. The second equation says J equals 3 over 2L minus 2, right? The left-hand side is J, right? And there are 5 binary joints in that arrangement that we're dealing with, right? How about the right-hand side? The right-hand side says that 3 over 2 times your number of links. We subtract 2 from that to find the value we're looking for. So that's 3 over 2 times, how many links are there? 5 links. Then we take 2 out of that, right? Let's look at this math. 3 times 5 is 15. If you divide that by 2, you have 7.5. If you subtract 2 from 7.5, you have 5.5. Okay? And you look at the left-hand side is 5. The right-hand side is 5.5. So again, the left-hand side is less than, okay, is less than the right-hand side. And so we can conclude that the second arrangement is an unconstrained or a non-kinematic chain. Okay, so that brings us to the end of that example. Now let's do another interesting one. I'm presuming that you are following me carefully. So let's do the third example. We are dealing with example 3, and we are to determine the nature of the given chain, right? And which chain are we dealing with? This one. All right, so let's watch very carefully. Let's determine the links. How many links are here? Follow me. Mostly some of these ones are labeled. I may not always label them, okay? Between A and B, there's 1 link. This is the second link between B and C, C and D. The third link, fourth. 5th, and 6th. So there are 6 links. There are 6 links. Okay. How about binary joins? Binary joins. Okay. Let's check. Binary joins J. How many J's are there? Now, if you check, at point A connects 2 links. So that's a binary joint. Point B connects 2 links. That's the second binary joint. Point C connects 3 links. Okay, that's 1 ternary joint, right? Point D connects 2 links. That's the third binary joint, right? Point E connects 3 links. That's the second ternary joint. So in this arrangement, there are 3 binary joints and 2 ternary joints. Okay, so but we want the value of only binary joints. And remember, we said the number of binary joints in an arrangement in a joint is given as L minus 1, where L is the number of links connected to that joint, and then we subtract 1 from them. From our counting, there are 3 binary joints already, but we have 2 ternary. Oh my God, we have 2 ternary joints, right? Ternary means 3 links are joined to it. And if there are 3 links, the equation that we should have is that the number of links connected at that joint minus 1 will give us the number of binary joints, right? So this is going to be 3 plus 2 times 3 minus 1. Okay? This 3 here is, so follow me carefully. This 2 here is telling me that I have 2 joints in this arrangement that have 3 links connected to them, right? And for each of these 3 links, the number of binary joints there can be defined or gotten by subtracting 1 from the number of links that are connected to the joint. And so there are 3 links connected to each of those ternary joints. So if you subtract 1 from them, we should have the number of binary joints, right? So this becomes 3 plus 2 times 2, because 3 minus 1 is 2. 2 times 2 is 4. 4 plus 3 is 7. So in this arrangement, there are 7 binary joints. There are 7 binary joints. Now, how about pairs? How many lower pairs are there? When you look at all these joints, joint A, joint B, joint C, joint D, and joint E, they are all lower pairs, okay? They are all lower pairs because it looks like there are revolute, excuse me, joints at those points. So we simply count these joints. 1, 2, 3, 4, 5. Okay, there are 5 lower pairs in that arrangement. So now we have the values of L, J, and P. We can check to determine the nature of this chain. So we use the equation. The first equation is L equals 2P minus 4, right? Let's check the left-hand side of that equation, okay, which says L is, how many links do we have there? We have 6 links, right? There are 6 links in that arrangement. Let's check the right-hand side. The right-hand side says that 2P minus 2, that's what we're looking for. Minus 4, I beg your pardon. 2P minus 4. And 2 times P. How many lower pairs are there? There are 5 lower pairs. So 2 times 5 minus 4 is what we're looking for. All right. 2 times 5 is 10. 10 minus 4 is 6. So you see that the left-hand side is the same as the right-hand side. So obviously the left-hand side is the same as the right-hand side. Now let's check the other equation and see what about it. The other equation says J equals 3 over 2L minus 2, right? So we're dealing with the left-hand side. The left-hand side says J is 7. Don't forget, J is 7. And I took you through the process of determining that. J is 7, right? And that's the left-hand side. Now let's deal with the right-hand side. The right-hand side says that 3 over 2L minus 2, and that is 3 over 2 times L. How many links are there? There are six links, right? So we put 6 there and subtract 2 from it, right? So let's do the math. 3 times 6 is 18, right? 18 divided by 2 is 9. 9 minus 2 is 7, okay? So again, we can see very clearly that the left-hand side is the same as the right-hand side. And so the second arrangement, oh, no, it's not the second arrangement. This is just one. Determine the nature of the chain given. The chain given is a kinematic chain. That means it has constrained motion because for both equations that we tested, the left-hand side is the same as the right-hand side. Okay. Now I'm going to allow you unmute very quickly, and you will do this. You will do this one for me. This is a class work, right? Determine the nature of the chain given. Okay, so that's the chain given, right? That's the chain given. So question, let me get you guys to be able to unmute yourself. Great. So question, how many links? What's the value of L for this chain? What's the value of L for this chain? How many L's are there?
There are 11 links.
11 links. Excellent. Good. Now, how many J's are there? J is binary joints. How many binary joints are in that arrangement?
Just one.
No.
One binary joint.
No one. I know that you can recognize one, but if you followed what I did in a class, you know that it's more than one. Yes, I'm waiting for you. How many J's? All right.
2. Size 2.
No.
Just one J, sir.
No.
Size 1.
It's not one.
Are you sure it's not 1?
It's not one.
7.
7.
Not 7. No.
Size 4.
7. No.
13. 4.
It's not 4.
6.
It's not 6.
13.
You're now guessing. You're not 3. All right, follow my logic. Follow me carefully. See, you are forgetting what I taught you in class. I said that normally, please listen carefully. Normally, when you have only two links connected to a joint, we call that joint a binary joint, right? Right? But when you have three links connected to a joint, we call it a ternary joint. Now, in that ternary joint, there are binary joints inside. Okay? When you have three links, two are connected to themselves. One is connected to the other as well. When you have four links connected to a joint, we call it a quaternary joint. But in those four links, we can still split them up into binary joints. So we gave you an equation. We said in a given joint, the number of binary joints in that joint is given by the equation L minus 1, where L is the number of links connected. So put L minus 1 in your head and let's check.
Size 1. 30.
Just follow me. I've already said 1 is not the answer. I'm trying to explain and you're shouting 1, 1, 1. Just follow me. Now, look at the arrangement and let's start with D. And I'm starting there for a purpose. Now, at joint D, how many links are there?
2.
2 links, right? Apply the equation L minus 1. L minus 1. L is the number of links. So how many binary joints are at point D? 1. Keep that, hold that in your mind. Now let's come to point B. Point B, joint B. How many links are connected to joint B?
3.
3 links. So apply the formula L minus 1. 3 minus 1. How many binary joints are there?
2.
Add it to the one you had before. How many do we have now?
3.
3. All right. Let's move to point A. How many links are connected to point A?
3.
3.
Okay. So how many binary joints are there? 2. That's L minus 1. 2. So add 2 to the 3 you had before. How many now?
5.
5. Good. Let's move to point C. How many joints are connected to point C?
3
joints.
No.
4
How many links? I mean,
4
4 links.
4.
4 links, right? 1, 2, 3,
Yes, sir.
4. So how many binary joints are there? Apply the formula L minus 1.
3.
3. So add 3 to the 5 you had before. How many binary joints do we have now?
8.
8. Keep it in the cooler. Let's move to point G. How many links are connected at joint G?
4.
How many binary joints, therefore?
3.
3 binary joints if you use the formula L minus 1. Now, add that 3 to the 8 we had before. How many now?
12.
11. 11. Okay, so let's move to joint E. Joint E has how many links connected to it? 3. Okay, what's the equivalent? How many binary joints are there now? 2. Right? So 11 plus 2 is what? 13. Okay, then let's move to the last joint, which is joint F. How many links are connected to joint F?
3
So how many binary joints are there now? 2. So we add 2 to 13, right? So how many binary joints do we have all together? 15. Our J is 15. There are 15 binary joints in this arrangement. That's how you calculate it. Is it clear now?
Yes, sir.
Then you still have your P to calculate. When you look at your P, you now check, okay, how many of these joints are lower pairs? All of them are lower pairs. I cannot say higher pair. I'll show an example of a higher pair soon. So let's count them. 1, 2, 3, 4, 5, 6, 7. So there are 7 lower pairs. So P equals 7. So you have L equals 11, J equals 15, P equals 7. You go and test those 2 equations to see whether the left-hand side is the same as the right-hand side or not. This one, I will give as take-home assignment. Go and try it at home. Is that okay?
Yes, sir.
Yes, sir.
Right. That being said, oh, I thought I had one that had an example of a higher pair. Okay, that will come much later. All right, that being said, I'm going to switch back to my slides. Please mute yourselves back now. Can you mute yourself back?
Yeah, I have a question.
Okay.
Yes, my question is, those of us that we are trying to connect, the network here is bad. So, if it's possible, can you post the video of this current class on the group so that we can get it? Like me, I've been trying to join on several occasions. The network is disconnecting me.
All right, I'll think about it. But when you're asking questions, ask questions relevant to the class. This kind of question, you ask it after the class, not in between. Eh?
Okay, I'm sorry. Thank you, sir.
Okay, so we go back to our slides. Great. All right. So we have finished looking at the nature of kinematic chains. There could be locked kinematic chains. There could be these people, you don't understand English at all. When you are not talking, mute yourself. Okay, so let's look at the types of kinematic chains that we have. Okay, we have basically what we call a 4-bar chain, right? Oh my Lord. And then we have what we call a slider crank chain. I will look at these very, very quickly. Give me a minute. Let me touch one or two. The slider crank mechanism is actually an inversion of the 4-bar chain, right? But for a 4-bar chain, the 4-bar chain basically has it has 4 rigid links, okay? And they are connected in such a way that they form something that looks like a quadrilateral with 4 pinpoints. Okay, now each of those pinpoints, when you hear a pinpoint, it means that the joint is a revolute joint. It allows one member to rotate relative to the other. Okay, you will see that particularly for the when we are defining a mechanism. For a mechanism, well, let me not jump ahead of me. Let's just stick with the 4-bar chain. Okay, so when one of the link, okay, it's actually on this slide. Okay, when one of the links of your mechanism is of your 4-bar chain or any chain at all is fixed, then we call it a mechanism. Is that okay? We just defined the 4-bar chain. We said the 4-bar chain is an arrangement of links that allow relative motion between the links, and their motion, the motion of those links is successfully or completely constrained. What that means is we can predict exactly how that link will move. Okay? If you make one of the links to move, we can predict or we know exactly how the other links move. That is a kinematic chain, right? Now, if one of the links in the chain is fixed, is made rigid, that itself does not move, all the others will move relative to themselves and to itself. Then that kinematic chain becomes a mechanism. Okay? So all mechanisms are kinematic chains, but not all kinematic chains are mechanisms. If you have a mechanism, if you have a kinematic chain and you fix one of the links, then it becomes a mechanism. But if you have a kinematic chain without any of the links fixed, then it is a kinematic chain. It is not a mechanism. Is that okay? And so in the 4-bar chain, the 4-bar chain is particularly designed in such a way that the links, and this is determined by the length of the links, right? One of the links is fixed, and we usually say that is the first link. You fix link number 1, right? Then you have a link that is short enough and is allowed to exhibit a complete revolution. So it is able to go round completely. Okay, and we call that link the crank. Then there is another link that is opposite to the crank that is allowed to move back and forth. It exhibits something like simple harmonic motion, right? Oh, it exhibits a simple harmonic motion, so it goes back and forth, and that link is called the rocker. Okay, it's called the rocker. Then there is the fourth link that connects the rocker or the lever, and that link is called the connecting rod. So this is the kind of thing, and one example is your piston. Your connecting rod, and the crankshaft inside your engine. It is a 4-bar chain. Okay, so when the crank rotates, this is the crank here as link number 2. When this rotates, right, it allows the connecting rod to transmit that motion between it and the rocker. And what the rocker does is the rocker will move back and forth. It oscillates back and forth. Now, there are several modifications that we can make of the 4-bar chain. Okay, if you look at all of these guys, they are all 4-bar chains. If you look at the first one, okay, this is a case of a crank and rocker mechanism. So as this crank here, the link AB, as it rotates, is going to cause link CD, which is the rocker, to rock back and forth. All right, you have a similar thing in this arrangement here, but this arrangement and this arrangement, they are arranged differently, but they are all still crank and rocker mechanisms. Okay, this one here, your rocker is up. This one here, the rocker is down. And obviously, you see that the connecting rod in this second case is longer than the connecting rod in the first case. All right. For this case, this is a case of a crank and crank. Okay, when your second link is the same as your fourth link, that allows for both of these links to rotate, and then the connecting rod will just transmit that motion between both of them. So the crank rotates. The one that should have been the rocker, because it's the same length as the crank, it also becomes a crank and also rotates. You will find this arrangement applied in locomotives, in trains, the wheel of trains. You find that they are connected by a crank and crank 4-bar chain. Is that okay? Few examples more of 4-bar chains. I don't have time to dwell on all of this. Now, when you look at the slider crank chain, the slider crank chain is actually a 4-bar chain, right? But instead of having a rocker, what it has a sliding pair. Okay? It has a sliding pair instead of the rocker, and then it has 3 turning pairs. So you will see that one pair is fixed. The second, one link is fixed. Okay, whichever aspects of this that is fixed is one link, right? This crank here is the second link. That one rotates round and round, and then this connecting rod connects the crank to your piston. Your piston is the slider, is the one that has a sliding pair. So as the crank goes round, it will push this piston forwards and backwards as that mechanism goes round and round. Okay, so this is a schematic of it. This is various motions that your four-bar chain exhibits. Now, I'm going to stop sharing this, and I'll quickly play you a video. I hope I saved that video. Yeah, I'll quickly play you a video that shows different chains, different mechanisms, and how they work connected one to another. Okay. Give me a minute. I will get. Is it this one I want to play now? Oh, that's a long one. Okay, I think I should try this. So let's play using this. Let me just check that. All right, it's the one I want to show. I'm going to move it here and share my screen. Sharing screen 2. And I want to share with audio. Here's sound. Okay. Share. Can you see my screen now? Oh, you can't speak. All right. I've muted all of you. I assume that you can see it. you can check out Praveen Singh. It's an Indian guy that created that video. You can check out his channel on YouTube to appreciate a lot on what mechanisms are and how we can visualize them. Okay, very, very important. How you arrange your linkages or your links, where you pin them together, and all of that will determine how they operate, how they move round and round. Okay, so I will move on to something else very quickly. Let's look at a few criteria, a few laws that govern some of these mechanisms. Okay, let's first define what a degree of freedom is and what the mobility of a mechanism is. So we're moving on to looking at terminologies around mechanisms, right? I remember we said the mechanism is a 4-bar chain. A mechanism is a 4-bar chain that has one of its links fixed, or any kinematic chain at all. Any kinematic chain that has one of the links fixed is a mechanism. And you see that all the other videos that we showed you different kinds of arrangements that the motion of one part of those links is allowing for and constraining the whole system, the whole arrangement to move in a particular way, right? In a particular way. Now, when you have a rigid body that is free to move anyhow it wants to move in space, right? You can define that movement either based on a translation along any of the 3 coordinate systems that we have, if you are using a Cartesian system to define your 3D space, right? Then an unconstrained motion of a rigid body will be described in relation to 1, translation along any of those axes, and 2, the rotation of that body about those axes. It doesn't matter the form and nature of movement of that rigid body. We can break it down into 6 motions: translation along x-axis, translation along y-axis, translation along z-axis, then rotation along rotation about x-axis, rotation about y-axis, and rotation about z-axis. And if you do that, you will describe completely how that rigid body moves. So when we define the degree of freedom, okay, we say that such a body that moves freely in space, as we've said, that we can define its motion, we can break down its motion into 6 parts. A translation, linear translation along x, y, and z axis, that's 3. And then rotation about x, y, and z axis, that's another 3. So we say it has 6 degrees of freedom. 6 degrees of freedom. It is free to move in 6 different ways. Its motion can be broken down into a movement in 6 that is described in those 6 ways that we've mentioned. So we define the degree of freedom of a mechanism as the number of inputs or the number of independent coordinates. So that's what we did in the introduction to degrees of freedom. We had 6 different ways, coordinates that this thing could move, or the number of relative motions that are required to completely describe the motion and the position of all the links in that mechanism at any given time with respect to the fixed link. I will say that again. It sounds long, but a degree of freedom, the degree of freedom of a mechanism, we are talking about how many different inputs do we need, how many different parameters, how many different relative motions do we need to do we need to completely describe the position of that mechanism at any point in time with respect to the fixed link? So for the 4-bar chain, for example, at any time, okay, how many inputs will you need to describe the links, the position of the links on that mechanism with respect to the fixed one, such that you would have described the position of all the links? You would have described, therefore, the state and the status of that mechanism. That's what we call the degree of freedom. Okay? And you can reduce the degree of freedom of a particular mechanism by constraining or stopping one of the links from moving. Okay? If you restrain the ability of that mechanism to move in a particular direction, then you would have reduced its degree of freedom. So like we said, for a rigid body that is allowed to move freely, unconstrained, it can translate along the x-axis, it can translate along the y-axis, it can translate along the z-axis, right? It can also rotate about the x-axis, it can also rotate about the y-axis, and it can also rotate about the z-axis. Now, if you prevent that body from moving in any of these 6 directions or ways that we've described, then you've reduced its ability to move generally by a degree. And so you'd have reduced its degree of freedom. So if you stop it from moving along the x-axis, from translating along the x-axis, then it now has 6 degrees of freedom. It means that it's not permitted to move along the x-axis. So if we want to define its position, we will need to tell how far did it move along the y-axis, how far did it move along the z-axis, did it also turn about the x-axis, did it turn about the y-axis, did it turn about the z-axis. We need 5 of those to describe completely where that body now is at that instance in time. So that's what degrees of freedom is, the number of inputs you need to define completely the position of all the links in that mechanism relative to the fixed link. Okay? Now, so in a mechanism, we say one link should always be fixed, right? And so the total number of movable links in the mechanism is n minus 1, where n is the number of links. Okay? Now I've moved to n. We can as well use that as L. Remember, we were using L as the number of links before. So if you have a mechanism and there are L or N links in that mechanism, then we say that the total number of movable links, since it's a mechanism, one link must be fixed, right? Then the number of movable links would be L or N minus 1. Now, what about mobility? When can we say a kinematic chain has fulfilled the condition for mobility? That it is mobile, it can move. So we have an equation, and this is not different from what we had before. We only modified it. Remember the equations? We had 2 equations that we're using to test whether an arrangement is a kinematic chain, a locked chain, or a non-kinematic chain. And you almost recognize it here. N here is the same as L as we had before. L equals 2p minus 4, which should be the same thing as 2j plus 2 all over 3. Okay? Both of these are amalgamated from those 2 equations. L equals to 2p minus 4 and j equals to 3 over 2L minus 2. Okay? So we have these 2 equations where N is the number of links and P is a number of lower pairs and J is the number of binary joins. All right? Now, there is now what we call the Kutzbach criterion. Okay? And the Kutzbach criterion says that the degree of freedom in a given mechanism, right, is defined by this equation here, which says that N, if N is the degree of freedom, right, or you can simply just call it DOF, is given by 3 bracket open L minus 1 minus 2J minus H. Now, follow me carefully. L here is the number of links in that mechanism. J is the number of binary joints, right? The number of binary joints or the number of lower pairs in the joint. And H is the number of higher pairs in that joint. Okay? So that's the definition. So when we start calculating, we want to apply the Kutzbach criterion to check that does this mechanism, how many degrees of freedom does this mechanism have? We use this equation. Now, if you use this equation, n equals to 3 bracket open L minus 2 bracket close minus 2J minus H. If you employ that for a mechanism and you find that the degree of freedom is 0, that means that linkage is a structure. It's immovable. Okay, it's a locked chain. So this is very similar to what we did with kinematic chains, but that was just kinematic chain. Now we're dealing with mechanisms where one of the links is fixed. If DOF is 0, then it's a structure, which is equivalent to the locked chain thing that we're dealing with before. If it has a degree of freedom of 1, then the mechanism can be driven by a single input motion. You just need to move one of the linkages and all the other linkages, or links rather, will move, okay, completely relative to the input that you've made. If it has a degree of freedom of 2, what that means is you need 2 separate input motions to produce the desired and the constrained motion that you want in that mechanism. Okay, so these are the conditions for mobility. If your degree of freedom is -1 or less, that means that there are certain redundant constraints in that chain that makes it become difficult to determine. It's a structure that is statically indeterminate. We can't decide how it moves, whether it moves, and all of that. Is that okay? So note these 3 conditions. Degree of freedom equals to 0 using the equation that says that n equals 3 bracket open L minus 1 bracket close minus 2J minus H, right? If the degree of freedom is 1, one single input will describe the motion of that whole mechanism. If the degree of freedom is 2, then you need 2 different inputs to describe the motion of that mechanism completely. And if the degree of freedom is -1 or less, then the structure is statically indeterminate. Okay, we cannot determine. So let's do examples again. So I'm going to stop sharing this so that I can get back to my Word document. We'll do that example. This class is 2 hours, right? So we'll stop at 12. We'll stop at 12 wherever we stop. Give me a minute. Let me find. Okay. So we did how many examples? Example 3. So this is example 4 now. Example 4. I want you to determine the degree of freedom of the mechanism shown below, right? I mean the degree of freedom of this mechanism here. Okay, so again, we would need to know how many J's, how many L's, how many H's are there. All right. So again, L is the number of links, J is the number of binary joints, and H is the number of higher pairs. So let's follow it very quickly. How many joints are here? 1, 2, 3, 4, 5. Okay, so I can say that, or I say joints, links, I beg your pardon. There are 5 links. How about binary joints? Let's check. How many binary joints are here? B and D are pure binary joints. They have only 2 links, right? A and C are ternary joints. They have 3 links connected to them. So at A and at C, the equivalent binary joint there will be 3 links minus 1, which is 2. So there are 2 binary joints here, 2 binary joints. That makes it 4, right? And then there is 1 there and 1 here. That makes it 6, okay? So we would say that J is 6, right? And H, how many higher pairs are here? There are no higher pairs. All these joints, A, B, C, and D, they are all lower pair joints. So H is 0, right? So what's the equation that we are going to use? So we are using the Kutzbach criterion to determine this criterion. And it says that the degree of freedom, which you can represent it as n, is given as 3 into L minus 1, right? Minus 2J minus H. Minus 2J minus H, right? That's what the equation is. So it means that n, or your degree of freedom, is given as 3 bracket open. How many links are there? 5 minus 1 bracket close minus 2 times J. How many J's are there? 6 minus what? Minus H, which is 0, right? So 5 minus 1 is 4. 4 times 3 is 12, right? And then you have, what's it called there? 2 times 6 is also 12. 12 minus 12 is 0. 0 minus 0 is 0. And so the degree of freedom of this mechanism is 0. So that means that, the given mechanism, right, is immovable. It can't move because the degree of freedom is 0. It's immovable, and hence, it is a structure. Okay, did you follow to that point? Again, very, very, very simple. The first thing you need to do is to identify or to deduce the parameters that you need: the number of links, the number of binary joints, and the number of higher pairs, right? And then we plug those into the Kutzbach criterion, which states that the degree of freedom of a given mechanism is given by this equation: 3 into L minus 1 minus 2J minus H. Plug in your values and evaluate them. Whatever value you have will determine, based on the things we said before. If DOF is 0, the structure is immovable, right? If it's 1, that means it requires 1 input to produce a constrained motion of the mechanism. If it's 2, it requires 2 inputs to produce a constrained motion of the mechanism. And if it's minus 1 or less, that means it is statically indeterminate. We can't define what is movement or how many inputs it would require. Okay, now let's do a second example on this topic. Okay. Okay, now example 5. Okay, and determine again the degree of freedom in the given mechanism. Okay. So this is the mechanism we're dealing with. Okay. So when you look, you will count how many links are there. Anytime you see this this shaded this thing at the bottom of something, it means that that thing is fixed to something. Whatever it is fixed to, that is your first link. So this and this together here, they are link 1. They are the fixed structure that all the other links are connected to, right? That's link 1. Then you have link 2, link 3, link 4, and link 5. And so for this question, we can, oh dear me, we can say that L, no, that's not what I want, excuse me. We can say that L is 5, right? How about J? How many binary joints are here? Okay. Link 5 is connected to link 1. That's a binary joint because it allows for revolute motion along, well, it's a lower pair and it's a binary joint. This is also a binary joint, 2 links. This is a binary joint, 2 links. That's a binary joint, 2 links. And this is a binary joint, 2 links, right? All of these joints are lower pairs. There is no higher pair. So J here is 1, 2, 3, 4, 5. There are 5 binary joints and there are no higher pairs. There are no higher pairs. So this should be pretty straightforward to find the degree of freedom. The degree of freedom can be found by this equation: 3 into L minus 1 minus 2J minus H, right? So the degree of freedom for that mechanism is going to be 3 bracket open. How many links are there? 5 links minus 1 bracket close minus 2 times how many binary joints are there? 5 also, minus H. H is the number of higher pairs. There are no higher pairs, right? So if you do that math, the degree of freedom is 5 minus 1 is 4. 4 times 3 is 12. 2 times 5 is 10. 12 minus 10 is 2. 2 minus 0 is 2. All right? And so this is a mechanism. This is a mechanism that requires 2, okay, 2 inputs to define the motion of the mechanism. Mechanism. So when you look at this, you can see obviously, you can see those 2 arrows here that you need to impute motion into link, or you need to define the motions of link 2 and link 5 to determine the overall position of every link in this mechanism. You must define how link 2 is positioned and how link 5 is positioned to determine the position of all the other links in the mechanism. So it has 2 degrees of freedom. Okay. Francis Gabriel, can you stop touching your screen? I don't know how many times you want me to beg you not to touch your screen. Okay, let's do another example. We need to find the degree of freedom of this. This is example 6, I think. Let's find the degree of freedom of this mechanism. Now, this can be very confusing. So follow. Oh, why did I? Oh, dear me. Okay. I need to move this guy out of here. It's in between. Yeah, great. So let's find the degree of freedom of this guy. So let's check. What are the links that are here? Now, notice that this link here is a ternary link, right? It's a link that can be connected, that has three joints on it, 3 points where other links can be connected to it. Okay, so they've used that shading there shows that it is one piece. So you even see the arrow telling us that this triangle here is one link. this one here is another link. So if you count the links, there are 1, 2. Link 2 connects link 1 to link 3, right? Link 4 connects link 3 to link 1. Link 5 connects link 3 to link 6, right? And then like that. So how many links are there? 1, 2, 3, 4, 5, 6. So there are 6 links. How about binary joints? Let's check. This joint here is a binary joint because it connects link 6 to link 1, right? It's easy to see that this link here is binary. I mean, this joint here is binary because it's connecting link 5 and 6. This joint here is also binary. That's the third one because it's connecting only link 5 to link 3. This one here is the fourth binary joint because it's connecting link 3 to link 4. This one here is also a binary joint. That's the fifth one because it's connecting link 1 and link 4. This guy here is the sixth binary joint. It's connecting link 1 and link 2. And then finally, this guy here is the seventh binary joint because it's connecting link 2 and link 3. They are all binary joints. And so J is 7, right? And then when you look at all of those guys, they are all lower pairs, all of them. They are all pin-like joints, so they are all lower pairs. So again, H here is 0. So you get the gist. You can easily find the degree of freedom like so. The degree of freedom is found by this equation, 3 into L minus 1, bracket close, minus 2J minus H, right? And that means that your degree of freedom is 3 times, how many links are there? 6 minus 1, bracket close, minus 2 times, how many binary joints are there? 7 minus 0 because there are no higher pairs, okay? So this automatically gives us a DOF of 6 minus 1 is 5. 5 times 3 is 15 minus 2 times 7. 2 times 7 is 14. So 15 minus 14, that's 1. 1 minus 0, that's 1. So this guy has just 1 degree of freedom, right? Let me look. Let's see. Let's do. Let me see. I think that one you can do that one as. Maybe I should use this as example. Let me see. Are you allowed to unmute yourselves? Let me allow you to unmute yourselves. Now this one will be class work. You will tell me the number of class work. Determine the degree of freedom of the given mechanism, right? So, question. How many links do you have? These things are easy because they tell you. In exam, you won't see all these numbers. So they just be the mechanism straight up. How many links do we have? You can unmute yourself and speak.
6.
6 links, correct? Correct. How many binary joints do we have? How many binary joints do we have?
4.
Nope.
2, 3, 6. 8 binary joints.
No, 8 is too much. They have even done it for you. Look, if you look at every joint, it tells you the links that are connected to that joint, right? This one here connects link 1 and 2. This joint here connects link 1 and 6. This joint here connects link 3 and 6. So you can easily tell which ones are binary. It's only this link that I mean, this joint that has 3 links connected to it, and I've taught you how to get the number of binary joints per link. Is that okay? So here, that's 1 binary, 2 binary, 3, 4, 5. Now, when you get here, there are 3 links connected. You apply the formula L minus 1. So how many binary joints are here? How many binary joints are there?
Seven binary joints.
There are 7 altogether. All right? There are 7.
Yes,
And
sir.
again, there are no higher pairs here. So you just plug it into your equation and you make progress. Okay. Let me see. Oh. All right.
Two.
I have 4 minutes before I finish. So I will define, I'm going to stop sharing this, and I'm going to go back to my slides so that I can define 1 or 2 things quickly before I go. 4 minutes to the end of the class, right? Okay, I will show you an where's my Zoom again? Am I still here? Yes, I am. Okay, let's share the seconds. All right, now, yeah, you can see my screen now. Great. So you see an example of a higher pair, okay? There's an example of a higher pair. When you look at this arrangement here, your first link is the one that is fixed. Your second link is this follower. And then your third link is this scam. This one here, when you see that there, that tells you, that dot there tells you that there is a revolute joint. This guy is allowed to rotate around with respect to this link 1. Link 2 is also allowed. It can produce either revolute oscillatory motion, okay? But it's about that point. That's a pin. It can move back and forth relative to this one. But when you look at the connection between 3 and 2, it's not a pin. There is a line contact or a point contact between them. These 3 and 2 form a higher pair. So when you are counting, you see that L is 3, 1, 2, 3. J is 2, right? There are 2 binary joints, this and this. This guy here is, and binary joints are particularly found with lower pairs, right? This one here is not a binary joint. It is a higher pair. So the higher pair there is 1. And so you can plug it into your equation and calculate to find your degree of freedom. Same thing here, okay? You have your links, link 1, 2, 3, and the wheel is the 4th link, right? The wheel 4 and 3, they are connected via a binary joint, right? That's a revolute joint right there. 3 and 2 has a binary joint. 2 and 1 has a binary joint, right? But between 4 and 1 is a line contact. That's a higher pair. Okay? So the same thing, you can impute those into the equation, and you see that this mechanism here has this thing. So let's quickly do 2 things and we'll end this class. Okay. If you apply the Kutzbach criterion to a planar mechanism, a mechanism that only moves on a plane, so the motion of that mechanism is constrained to a plane. It does not engage, or its motion is not 3-dimensional. Is on a plane. Then you can modify the Kutzbach criterion to become a criterion called the Grobler's. So it's the same thing, but only that you have the what's it called now? The equation now becomes the Grobler's equation. So with the Grobler's equation, you apply that to only mechanisms that have 1 degree of freedom. Okay. So in this equation, where we see n, which is the number of degrees of freedom, we put 1. Okay. And then there are no higher pairs. there are no higher pairs with the Grobler equation. So we put H there. We put 0. So if here is 1 and here is 0, if you rearrange the equation, you arrive at this. Okay, that L equals 3. That should not be L, that should be 1. That should be 1. Okay, because we are saying that the degree of freedom here is 1. 1 equals 3 into L minus 1 minus 2J. This becomes 0, right? And when you rearrange that, you have this equation, because you open this bracket, 3 times L. So I've closed my, this I would have shown you. 3 times L is 3L. 3 times minus 1 is minus 3, right? And then you have minus 2J. If you bring this 1, this is 1. If you bring 1 this way, minus 3, that will become minus. Minus 3 minus 1 will be minus 4 that you are seeing here. And then that 3L will be there, and then minus 2J will be there. This is what is called the Grobler's criterion. Is that okay? The Grobler's criterion. Finally, before I go, it's already 12 minutes past. Or when I come back, if I start this, I won't finish it. When we come next time, we will look at the Grashoff's law. Let me quickly see how far I have. Can I do the Grashoff? I think I can do the Grashoff's law. Okay, let me do the Grashoff's law before I go. Now, the Grashoff's law states that, and this is particularly applicable to the 4-bar chain. The 4-bar chain, the 4-bar mechanism, exactly. So Grashoff's law states that for a 4-bar chain, right? For a 4-bar chain to have continuous relative motion between the links, then the sum of the shortest and the longest links must not be greater than the sum of the remaining 2 links. Okay? To have continuous relative motion between the crank and the rocker, between the two, because it has 2 degrees of freedom, between the 2 input motion, then the sum of the shortest and the longest links must not be greater than, they must be less than or equal to the sum of the remaining 2 links. So when you look at this criterion here, the shortest link is this S here. That's the crank. The crank is almost always the shortest link. For this particular arrangement, the longest link here is this L. That's your rocker. So we take the shortest link and add to the longest link, okay, L plus S. And the value you get must be less than or equal to the sum of the remaining 2 links. So the remaining 2 links will be P and Q. If it's greater than, that means that there will not be continuous relative motion between those 2 guys. Is that okay? Okay. So we say that to ensure that the input crank continues to make a complete revolution relative to the other links, then that criterion must be met. Okay? Where the sum of the shortest link, which is always the crank, should, and the sum of that shortest link and whichever other link is the longest link, right? That sum should be less than or equals to the sum of the other 2 remaining links if you will achieve that motion. Okay? So again, Grashoff's law states that for a 4-bar mechanism to have continuous relative motion between the 2 input links, then the sum of the shortest and the longest link in the mechanism must not be greater than the sum of the 2 remaining links. All right, I will stop there for today. And if you have any questions, you can ask very quickly before I go. Any questions? No questions. All right. I will try and put this this class we've had on my YouTube channel. Then I will send you guys the link, because this video they usually are very large. If I say I will send it to you on WhatsApp, send it to you on this, it will be difficult. I'll just put it on YouTube, and you can always access it, at least for this semester. And then after the semester, I can take it down. So I will try and do that at some point next week. This week is choked for me. I'll try and do that at some point next week. And hopefully by next week, I should be back in class in person. If again, I can't come in person next week, then we might now have to still continue with the online class. Okay. Usually I would have asked you guys which ones do you prefer, but people generally prefer in person, so we'll come in person. Each method has its own advantage and it has its own disadvantage. One advantage of this is that, okay, you have access to the videos thereafter, right? To always go back and as a form of revision. But when we come in class and we talk in person in class, you can't go back and listen to what we've done in class. Okay, so all right. God bless you all, and we'll see you next week.
All right. Have a nice day, sir.